What do these polynomials have in common? Okay, on the screen, like there are three different kind of polynomials. This polynomial with subscript p, they stand for Legendre polynomials. The polynomials with the notation h stands for Hermite polynomials, and the polynomial with notation L stands for Laguerre polynomials. And the question is, what do they have in common? And the answer is the fact that all of these polynomials are actually orthogonal to each other in their set. So basically over here, P naught x is orthogonal to P1x, which is also orthogonal to P2x, which is which is also orthogonal to P3x, and so on, right? And I think from vectors you might have known that if if like the some things are like orthogonal, they can form a basis, right? So what do these form basis of? Then the answer is this polynomials, like each of these set of polynomials, either Laguerre or Legendre or Hermite, they come as a solution of some differential equations. And the differential equations are from like quantum mechanics, right? Like while solving for the radial part of hydrogen atom, or like harmonic oscillator, or like something similar. So in quantum mechanics, like to solve those differential equations, like these sort of polynomials are the solutions, and the ones that are given here, like each of the set is actually consist of the orthogonal set of polynomials, which can form the basis. And then in this video, like we will talk about what does it mean for like two polynomials to be orthogonal, and we'll also verify that each of this set actually contains the orthogonal set of polynomials, right? So that will be the goal of this video. It's a pretty easy video. I think we'll just verify their properties of orthogonality. So what does it mean for like two polynomials to be orthogonal, right? So the idea is that, so let's say if I have a polynomial, let's say p of x and q of x, so their orthogonality, like in like vector, we just take dot product, right? But over here, we take the integration. So if the integration from a to b of p of x with q of x dx, if this is 0, then we say that p of x and q of x are orthogonal to each other. And note that this is also specific to certain interval. So on AB, right? On AB. Okay, so yeah, now the thing is that this orthogonality depends on the interval as well, right? So like sometimes it can be like -1 to 1 or 0 to infinity or -infinity to infinity. It can be anything. So it depends on the interval. And also there we can also extend this idea like to the idea of orthogonality with respect to some weights. Orthogonality with respect to some weights, right? So how that works is, along with these two polynomials, we will also have some weights, let's say w of x, and with that weight, their integral becomes 0. And in this case, they are also orthogonal with respect to some weights w. Now, I will just tell you, now these Legendre polynomials, they are like, their orthogonality is like this. For Legendre polynomial, the orthogonality will be such that the integral from -1 to 1 or Pm of x, Pn of x dx is equals to 0. This condition, and this is only if m is not equals to n. Okay? So yeah. So these are like, they are not orthogonal to itself, but they're orthogonal to each other. That's how it works. Like if you just take the same thing, then you actually get the magnitude square. Just like in vector, if you take the dot product of the same thing, you get the magnitude square, right? Over here also, if you take the same like p over here from here, let's say p1 and p1, then you just get the magnitude of p1 square. It's the same idea. So this is how the orthogonality defined, and you can also actually use this orthogonality condition to actually find all of them. So how you can do is, okay, now these polynomials, since they're orthogonal to each other, that also means that, let's say if I just choose P2, this P2 has to be orthogonal to both 1 and x, right? So you can try to find a polynomial in the form, let's say ax squared plus bx plus c, which is orthogonal to both 1 and x. And in that way, you will get system of equation, and then you can solve for P2 of x. Even if you want to find like P3, this P3 also has to be orthogonal to both 1, x, as well as x squared, right? And then because over here in P2, like this is 3 over 2 x squared minus 1 over 2, right? And because P3 is already orthogonal to 1, it will be orthogonal to 1 over 2. That's why P3 also has to be orthogonal to 3 over 2 x squared, and hence x squared as well. So the idea is like, if you take, let's say P5 of x, it will be orthogonal to like all the like 1 x square x cube x to the power 4, right? And then so what you can do is, if you know that thing, you can just take a general fifth order polynomial and then just integrate with like 1 x square x cube x to the power 4, and each of them should be 0, and you get a system of equation, and then you can solve for a b c d all of them. So you can also use this orthogonality property to actually find these polynomials, but there are also other better ways you can use. Okay, so enough about that. So let me also write orthogonality condition for the other ones, and we will verify them. Verifying them is actually the goal of this video. For Hermite polynomials, the orthogonality condition is that from minus infinity to infinity, and then there will be a weight which is e to the power minus x square. And if you take these two Hermite polynomials, the integral will just be 0. And for the Laguerre polynomials, the condition is that integral from 0 to infinity with e to the power minus x, and then L sub mx, ln sub x, dx will be 0. And this, all of them should need to have m not equals to n, right? Okay, so we'll just try to verify that the orthogonality condition is true in this set. And then that's really interesting, right? Like for like polynomials, and then like orthogonal polynomials, that's abstract, but like it works the same way, like being a basis, things like that. Yeah, okay. So let's take P2 and P3, or is that too tough? I don't think so. Okay, I mean, but it takes some time. Let's take P2 and P3, even though the multiplication can be a bit long. Okay, half 3x squared minus 1. P2 of x is equals to half 3x squared minus 1, and then half 5x cubed minus 3x, half 5x cubed minus 3x, right? 5x cubed minus 3x. Okay, so we want to verify that the integral from minus 1 to 1, P2 of x, P3 of x is equals to 0, right? So minus 1 to 1, this is, I don't actually need half, right? Because it doesn't matter. 5x cubed minus 3x dx, right? So I can just take the half outside, and then this becomes 15x to the power 5 minus 9x cubed minus 5x cubed plus 3x dx, right? So now this becomes 15 times x to the power 6 over 6, and that will just be 0 because it's odd function. So okay, actually all of them are odd functions, so that will just be 0. This one was so simple. So this is just 0. Okay, so I got actually very easy case, right? And you like, even if this, it doesn't really cancel this way, let's say if I take p1 of x, which is just x, right? If I take p1 of x, which is just x, in this case it doesn't cancel, right? And then I take p1 of x with p3 of x, I will have 5x to the power 4 minus 3x squared dx, right? So in this case, this is x to the power 5 minus x cubed. Now this also cancels because it's just 1 minus 1 minus 1 plus 1. Okay, so all of them are easy cases, but yeah, there can be like complicated stuff, and again, all of them like nicely cancel out. Okay, we verified for this, right? Okay, now let's go to the Hermite polynomials. Let's take 2x and 4x square minus 2. Let's take h1 of x equals to 2x and h2 of x is equals to 4x square minus 2. 2x and 4x square minus 2, right? Okay. And then what we need to do is for the Hermite polynomials, the orthogonality condition is minus infinity to infinity e to the power minus x square. Yeah. This one is a bit complicated, right? So e to the power minus x square with 2x and then 4x square minus 2 dx, right? Let's see. Okay, let me make a substitution u is equals to x. Okay, first of all, wait, I noticed something. What I noticed is that this can be written as 8x cubed minus 4x dx. Now this is just an odd function, so this will just be 0. This was simple. Okay, let's take something else. Um, let's take 1. Let's take as naught of x, which is just 1, right? And then again we'll try to verify that. Okay, in this case we are taking as 1 of x and as 2 of x. Let's take um minus infinity to infinity e to the power minus x square as naught of x with as 2 of x. Okay, so this will be minus infinity to infinity e to the power minus x square. This is just 1 and that's just 4x square minus 2 dx, right? So now this becomes integral from minus infinity to infinity of e to the power minus x square. Wait, I'm writing the same thing. So what you can actually do is you can make a u substitution u is equals to x square. Before that, you can notice that this is actually a symmetric integral. So we can write this as 0, integral from 0 to infinity e to the power minus x square, 4x square minus 2 dx. If you make a u substitution, u is equals to x square, we will have 2 integral from 0 to infinity e to the power minus u, 4u minus 2, right? And then half u to the power minus half du. So now this one simplifies to 0 to infinity of e to the power minus u, 4u to the power half minus 2u to the power minus half du. Now we can use gamma function. This will be gamma 3 over 2 minus 2 times gamma 1 over 2. This is 4 into 1 over 2 times root pi minus 2 times root pi, which is 0. And we notice that this actually is 0 and it works, right? Pretty interesting. Okay, so now the last one, the Lagrange polynomials, 0 to infinity. Okay, for Lagrange. 0 to infinity e to the power minus x, L1 of L m of x, lm sorry, and ln of x dx. Okay, so uh let's take L1 and L2. L1 is 1 minus x. L1 of x is 1 minus x, and L2 of x is x square minus 4x plus 2. Half of x square minus 4x plus 2. Okay, let's do the integral. 0 to infinity of e to the power minus x, 1 minus x, and then half x square minus 4x plus 2, right? Okay, so now if I can take the half, okay, I can take the half outside, and then I will have e to the power minus x. This looks so complicated. X square minus x cubed minus 4x plus 4x square plus 2 minus 2x dx, right? Yes, so x square minus x cubed minus 4x plus 4x square plus 2 minus 2x. Okay, half 0 to infinity e to the power minus x. Now this is 5x square. Also we have minus x cube, and then minus 6x plus 2 dx, right? Minus x cube plus 5x square minus 6x plus 2 dx. Okay, now we can use gamma function again. Half. This is 5 times gamma 3 minus gamma 4, right? Minus 6 gamma 2 plus 2 gamma 1, right? Okay, so half 10 minus 6 minus 6 plus 2, which is 12 minus 12, which is 0. And we see that they're also orthogonal to each other. And this is pretty satisfying, you know, like the fact that we are taking integral with like exponential or exponential squared, and then they nicely reduced to 0, right? To me, like this polynomial feels so special and like so like satisfying. And like that's why they also form the basis of the solution of the differential equation that arise in quantum mechanics. And like the person who thought of like the idea of making like these orthogonal polynomials and like how helpful they could be, that's really nice, bro. And yeah, so these were this, and then I think like so for some of you who had not heard of the orthogonal polynomials, I think for them it might have been helpful. Now they like know, and they also verified some orthogonal polynomials, and then the ways they can be orthogonal, like different intervals or different weights. Yeah, I hope it was helpful. And then for such helpful contents, definitely subscribe to the channel, and I look forward to seeing you in the upcoming videos too. Thanks for watching.